Okay, let's take a look at things that are going to be part of what we're working on next, which is the chemistry of solutions. Let's take a look at a familiar example, preparing some Kool-Aid. In this scenario, we have liquid water, which we'll identify as our solvent, and we're going to take some powdered Kool-Aid, Kool-Aid solid, and that's going to be our solute that we add to make our solution. When we mix the dissolved solid Kool-Aid or mix the solid Kool-Aid into the water, we're taking a solute and dissolving it into the solvent. This then creates for us a solution of Kool-Aid, where we now have the Kool-Aid dissolved in the solvent. This would be an aqueous solution of Kool-Aid. We now have a solution. Once again, the water is our solvent. The Kool-Aid solid, which we dissolved into the water, was our solute. We've created a solution of Kool-Aid. And the AQ here, the AQ stands for aqueous or dissolved in water. We've created an aqueous solution of Kool-Aid. Now the solute is what we're dissolving. The solvent is what the material is being dissolved into. Now let's take a look at how the solute-solvent interaction can influence some things such as the vapor pressure of a solution, and then ultimately what the boiling temperature of a solution is compared to pure solvent. In our picture at the far left, this is a scenario with what we've just finished with in our current unit that we just had, where we have something that's all solvent. It's one material, it's a liquid. That solvent will evaporate and will form gaseous particles of that solvent, and then we establish an equilibrium. When the equilibrium is reached, we have what we call our vapor pressure. Now let's say for this particular material that the vapor pressure at our given temperature is 100 millimeters of mercury, and we've established our vapor pressure inside this container. This represents again pure solvent. In the next scenario, we've now made a solution. If we could look at the particles, we'd see it's 80% solvent, 20% solute. In other words, if we could go for a swim and look around, we would see 8 particles of solvent and 2 particles that are solute for every 10 particles that we count. What this does now is, because there's fewer solvent particles, the number of solvent particles that can become gaseous becomes lesser. In this case, it goes down by, it's only 80% of what it would be if it was pure solvent. Consequently, when we reach our gaseous vapor pressure at the same temperature as this first scenario, our vapor pressure is now only going to be 80 millimeters mercury, when only 80% of our material is actually solvent. In our last example, we've now made a solution where we have 60% solvent, 40% solute. If we looked around, we'd see 6 particles of solvent, 4 particles of solute. Because there's now an even lesser amount of solvent particles, even fewer solvent particles can become gaseous at our given temperature, causing the vapor pressure to go down. The vapor pressure now would be 60% of what it is for pure solvent, because there's only 60% in our solution of solvent particles. Now for a solution, as with pure solvent, to make something boil, we have to hit the temperature. The boiling point, again, is a temperature at which the vapor pressure becomes equal to whatever the pressure or outside pressure is over the liquid. So in our first scenario, we'd have to increase the temperature to bring it from 100 to 760, the second one from 80 to 760, and in the third one we'd have to go from 60 all the way up to 760 to cause the solution to boil. As we can see, the change in pressure that we need to cross over to reach the outside pressure, as we go from pure solvent to a solution that's 80% solvent to a solution that's 60% solvent, the change in pressure goes from 660 millimeters mercury to 680 to 700. Consequently, the greater the gap in pressure that we have to reach to bring about boiling, the more energy we need to add to the system to cause boiling to happen. So as the solution becomes less and less solvent and the vapor pressure of that solution becomes less and less, the energy we have to add becomes more and more. So what we find is the temperature at which boiling happens becomes greater and greater. So of these three, the pure solvent would have the lowest boiling point, and then the temperature boiling of the 80% solvent solution would be higher than pure solvent, and then the one that's 60% solvent would be even higher. Because once again, as the fraction of solvent becomes less, the pressure at the vapor pressure becomes less. So to reach the outside pressure, the gap is larger, so we have to add more energy to cross that gap and bring the vapor pressure equal to the outside pressure. A larger gap requiring more energy means the temperature of the solution at which it boils will be higher than the temperature at which pure solvent boils. An equation that will be of note for these solvent and solutions is this particular equation. And what this is, P1 represents the vapor pressure of the solvent gaseous particles that exist over a solution. X1 is the mole fraction of solvent, and P1 with the little standard sign would be our vapor pressure of the gaseous solvent particles over pure solvent. Let's show how this works with each of our sample solutions. If we have 100% solvent, our mole fraction of solvent would be 1, representing 100%. The vapor pressure of the pure solvent we had as 100 millimeters mercury, so the vapor pressure over this particular scenario would also be 100. For our solution number 2, our mole fraction for 80% solvent would be 0.8. That means we'd see 8 out of every 10 particles would be solvent. Our P1 with the degree sign is still 100 for the standard pure solvent vapor pressure, which now over the solution, the vapor pressure would become only 80 millimeters mercury. Once again, the vapor pressure goes down because there's fewer solvent particles that can become gaseous at a given temperature when the solution is made up of something where it's not 100% solvent. In the last scenario, our mole fraction of solvent is 0.6, representing 60% that's solvent particles. Our pure solvent is still 100 millimeters mercury, so the vapor pressure over this particular solution would end up being 60 millimeters mercury, which is less than the pure solvent, which is another reason why the boiling point now becomes higher for the solution compared to pure solvent. Now within the world of solutes, the material that we dissolve into a solvent, there's different types. Some can be identified as what we call electrolytes. Some are identified as non-electrolytes. Essentially, the distinction comes down to electrolytes are primarily ionic materials. Non-electrolytes would be materials that are molecular. The distinction between the two, if we look at something that's ionic, such as NaCl, when that gets dissolved into water, it separates into sodium ions and chloride ions. So the ions are now separate from each other. This allows for the flow of electricity. If we had a light bulb immersed in this solution, dipped into it, and tried to pass current to light the light bulb, with an electrolyte, we see that the light bulb will light up, indicating that there is current passing through the light. This is why this type of solution in the solute is known as an electrolyte, because it allows for the flow of electricity. A non-electrolyte, on the other hand, would be something that's molecular. When molecular compounds dissolve in water, the molecules remain intact. The molecules just get separated from one another. So what we have here is sugar, and we have neutral sugar molecules that are now surrounded by water and separated. The sugar molecules are separated from each other. It makes a sugar solution. But because it's contained of neutral molecules, this will not conduct electricity, and in this case, if we were to try to pass electricity through it, the light would not light up, which would indicate that our solute is something we categorize as a non-electrolyte. Now we have a couple equations that actually determine for us what the change in temperature will be of either boiling or also freezing, which changes for a solution relative to pure solvent. This is change in temperature boiling is a boiling constant, which for water is 0.52. M stands for something that's called molality, and the I here represents the number of pieces that our solute will break into when it gets dissolved. Now the freezing point depression constant for water is 1.86. Now the number of pieces is when the solute goes into the solvent and dissolves. For something that's a molecule, the I value is always going to be 1. This would be true for what we categorize as non-electrolytes. Now I will vary for things that we call electrolytes, because electrolytes being ionic, when they go into solution, can break into a different number of pieces. For example, NaCl will break into Na plus ions and Cl minus ions, so I would be equal to 2. Something like magnesium chloride, on the other hand, will break into a magnesium 2 plus and 2 chloride ions, so the value of I would be equal to 3. Something such as aluminum chloride, where aluminum is a 3 plus, this makes an aluminum ion and 3 chloride ions, so the value of I would be equal to 4. Now what this does, as the number of pieces of solute becomes greater, that means the mole fraction of solute becomes greater, so the mole fraction of solvent becomes lesser. Mole fraction of solvent becomes lesser, the amount of solvent that can become gaseous becomes lesser, so the vapor pressure of the solvent becomes lesser. So as you can see, the number of particles has an impact on ultimately what happens to the vapor pressure, which impacts how the boiling point or freezing point will be changed for the solution compared to the pure solvent. The small m in each of our equations is a unique unit of measure that's specific for these change in boiling and change in freezing point scenarios, which are known as colligative properties. It's something called molality. Now what molality is, it's the amount of moles of solute, the material being dissolved, divided by kilograms of solvent. This would be how one figures out the molality for a given solution. Now these particular things of changing the vapor pressure of a solvent by making it into a solution, and ultimately then changing the boiling point and freezing point of that material by making a solution, these are all something known as colligative properties. Key thing with colligative properties is they depend only on the number of particles, as we vary the mole fraction of solute and mole fraction of solvent. It's independent of what type of particle it is. It does not matter if the particles are molecules or ions, merely the number of particles that are solute and the number of particles that are solvent cause the change in vapor pressure, which changes the boiling point and freezing point.